So when I was a kid, they said, "Oh, it's like too small. It's like atomic. You can't actually vision how small that is. You can't see an atom." That's no longer the case. We can see atoms. In fact, in this first slide, you can actually see a whole series of copper atoms lined up with a little magnet at the end of a needle, essentially. So it's a microscopic needle that is magnetic, and it pushes the atoms around and forms things like you see here, which is a circle. If you want to, you can go to the IBM website. It's a link. It's called A Boy and His Atom. You'll see that actually on YouTube too if you look it up. So you can actually see atoms in a way. So we have a representation of these things. Actually are a finite sort of item that you can actually envision, so you can see it. Essentially, this is with a scanning electron microscope that they were able to do this sort of what seems to be magic, right? So it's like, times change. So here we have some atoms. So we're going to talk about atoms and molecules and how they form everything that essentially we have to study in geology, or we get to study in geology. So everything that we have is essentially either grown on the Earth's surface as a crop, either the trees or the plants that give us the food that we eat, or in the subsurface we have water, and that all comes from Earth, essentially, right? So we have soils that form from the rocks that are at the surface. And then also we have minerals that we can mine and extract all of the metallic things that we use for every computer, for every cell phone. There's all these metals that come from around the world. And then also the plastics that go into our modern world as well. All of that has to come from Earth. It doesn't come from outer space. We have oil wells that produce the petrochemical industry. We have mining that produces the copper and the lead, and all of these things that we have in geology is related to all that, right? These are all resources. So it's important for us to understand how they form and where they come from. And so to get an understanding of that, actually, we're going to have to take it back from knowing that we need those things. Is like, well, what are they really made out of? And so when we focus in on the finest details, we see atoms. And so atoms interact with one another. And so, and actually, if we have a group of atoms, we call it an element. So the smallest part of an element, and an element's this group of particles that all have the same appearance and behavior, the smallest indivisible part of that would be the atom. And so I like to use the analogy of like paper clips or binder clips or push pins. If you had a whole bunch of those and you shook them all up in a container and dumped them out on a table, and we're able to sort them out, right? Here's the push pins, here's the binder clips, here's the paper clips. And then you began to divide each one of those piles in half. So you'd have half of the push pins on one side. Take half of them away. Take half of the paper clips away. Take half of the binder clips away. When you finally get down there, it's like, oh, okay, there's 4 of each of these things left. So you take, 2 of the binder clips away and 2 of the push pins and 2 of the paper clips, and finally get down to 1. You have 1 of each. And so can you cut it in half, and is it still going to be a paper clip? Well, no, it's going to be half of a paper clip. It's not going to behave the same way that a paper clip does, or the push one the same way, right? Or the binder clip. So you're winding up with pieces of these things instead. So when it gets down to 1, that is the atom. So it's the smallest indivisible part of an element. And so when we look at atoms, we can say that they all have a few things in common. One of those is that an atom is going to have a nucleus, and then surrounding that nucleus, it's going to have an electron cloud. The electron cloud is where 1 or more, usually 2 or more electrons are spinning around and form essentially what is a racetrack around that nucleus. And so the nucleus can, in fact, be composed of 2 different kinds of particles. So in the nucleus, we find that there are neutrons and also protons. And the reason why these are all defined differently is because of a couple things. One of them is the charges that are on these things, and then one of them is the size of the weight. And so size-wise, protons and neutrons are almost identical. They weigh 1 each. And an electron is almost weightless, but because it's almost weightless, it has really rapid rates of speed, right, or velocity. And so it goes almost the speed of light, right? So these things are traveling very, very rapidly around that nucleus. So if the nucleus can have one or two different kinds of particles, it has at least one, that's a proton. Every single element, every atom has a proton in it. It may also have a neutron in it as well. And so that defines the nucleus. And the plural of that is nuclei, right? So you have more than one nucleus. You only have one nucleus for every atom, however. And so the nuclei have at least one proton. And then that proton, we by definition say it weighs 1. And a neutron weighs 1 as well. So what's the difference between a proton and a neutron? Well, a proton has a positive charge and a neutron has a neutral charge. And the negative charge is actually assigned to the electron, and the electron spinning around the outside is attracted to the proton. And so that makes up the core of what we know as an atom. So atoms, they can have a variable number of neutrons in their nuclei. And I like to illustrate this. Actually, the first guy who illustrated this was Niels Bohr. He was a Danish geophysicist. He was a physicist and a chemist, and he came up with what we call the Bohr model. It's a conceptual model. So he says, here's a circle that represents a proton, has a plus charge. Here's another proton, has a plus charge. Here's a neutron, has a neutral charge. Here's a neutron, has a neutral charge. And by doing that, he made the nucleus of a helium atom. And so helium has 2 protons and 2 neutrons. And surrounding that, in fact, in that cloud are 2 electrons. It's a very stable atom. And so that is what is in a helium atom. And so you get 2 protons, 2 neutrons, 2 electrons. It weighs 4 because the neutrons weigh 1 and the protons weigh 1. And there's 2 of each of those. So there's a weight of 4. And yet what defines it as helium is the fact that it has 2 protons. And so that is the atomic number of helium. And so it has an atomic number of 2 and atomic mass of 4. And so around that, again, is the electron cloud. And so the electron cloud is pretty tight around that. And so that is the standard for how we kind of define what an atom is. Hydrogen doesn't work that way quite. So we'll go into hydrogen a little bit more detail later. But helium has these 2 electrons in the electron cloud and 2 neutrons, 2 protons. And because these electrons are buzzing around that nucleus, they are actually spinning as they go around that nucleus. And so when they're spinning around that nucleus, one of them spins one direction, the other one spins the other direction. And so in other words, one's going this way and the other one's going the other way. But they're in this cloud that circles around that nucleus. And it was Werner Heisenberg, actually, that gave us the uncertainty principle. And he stated that, like, you may know what the spin is on the electrons, but you won't know where they're located. And so it's called the Heisenberg uncertainty principle. You may know Heisenberg from Breaking Bad, for all I know, but that's where that name came from. It's the Heisenberg uncertainty principle. And so if we have every element has different sort of properties. It has different appearance, perhaps, like gold looks gold, silver looks, you know what I mean? It's like every single one has something different about it, and that's based on the atomic number. And so every element has a different atomic number. That's the number of protons in the nucleus. And so atomic mass, however, is the protons plus the neutrons. And so if the number of protons defines the atomic number, the atomic mass is defined by the number of protons plus the number of neutrons. And let me give you some examples of this. So like carbon's a really good one because the atomic number for carbon is 6. And if you look at the atomic mass on a chart, you're going to see that the mass is 12.01 or 12.011. And so what that means is there's at least 6 neutrons in there, or 6 protons. That's what makes it carbon. To add up to 12, you have to add 6 more neutrons to be 12, right? And so, in fact, it's 12.011. And so when they try to determine the atomic mass, they actually have to take into account that sometimes there's an extra neutron in there. And that happens. You guys are familiar with this, actually. So you've heard of carbon-14 before. Well, carbon-14 is not carbon-12. There's 2 extra neutrons in there. As it turns out, those neutrons decay over time, and it turns into something else. But in fact, carbon-14 is what we call an isotope of carbon. And carbon-12 is an isotope of carbon as well. And actually, there's a carbon-13 that's an isotope of carbon as well. That's regarded as a stable isotope of carbon. Carbon-12 is stable as well. Carbon-14 is not, however. It's radioactive. So carbon-13 and carbon-12 are both regarded as isotopes. And in fact, carbon-14 is an isotope as well. So an isotope is defined as an atom that has a variable number of neutrons in it. So this is important for us. And you're going to hear another word in just a minute here that's going to be easy to confuse with the idea or the concept of a variable number of neutrons in the nucleus, and that's called an ion. So we're going to come to that next here. But first, I have to tell you about how we organize atoms or elements in an understandable sort of universal way, and we call that the periodic table of elements. And the guy who came up with it was a Russian physicist or a Russian chemist, Mendeleev. And Mendeleev organized the elements in this sort of table that makes a lot of sense. We're going to zoom ahead to that table, and if you see the table here, you can see some of the elements that are identified by abbreviation. So in the upper left, you see H, which is helium. In the upper right, you can see, hydrogen. Hydrogen has an atomic number of 1. It's the lightest, the smallest you can possibly get on the periodic table. So hydrogen is the first. There is no element 0. Okay, it doesn't happen. So element with 1 proton in it, it's hydrogen. With 2, it's helium, as you well know. So that's in the upper right here. And of course, the mass for that is actually 4 because you have to add on to that 2 extra neutrons to that to make it with a mass of 4. But it's defined by the protons, and there are 2 of those. If you go to 3, you have to drop down and head back over to the left-hand side, and you see lithium there. Lithium is identified by the symbol Li. Next to that is beryllium. That has a number of 4. There are 4 protons in it. You have to skip over to get to 5 to the 13th column here, and that's just above aluminum is boron there. So B is boron, C is carbon, N is nitrogen, O is oxygen, F is fluorine, and at the end of that second row across is Ne or neon. And so if we head back over, third row now, we're looking at Na. Na is funny because that actually stands for natron, which is the Latin word for sodium. So that's sodium. Na is sodium. Mg is magnesium. Al is aluminum. Silicon is 14 here. You can see phosphorus is 15. Sulfur is 16. And 17 is chlorine. We're going to come back to chlorine later in this lecture. 18 over here is argon. Okay, so Mendeleev, when he was studying these elements, he says there are certain properties that they all have in common. For instance, if you take hydrogen, or if you take lithium, or if you take sodium, or below that, which is potassium, which is identified as a K. And so all of those have something in common. They're all very reactive. And if you go to the right-hand side, you go to helium, neon, argon, krypton, xenon, radon. All of those are non-reactive, in fact. So all of those are what we refer to as the noble gases. They are very well balanced. The number of electrons equals the number of protons in every one of those on the right-hand side. Those are called the noble gases. If you go over to that first column again, all of those, in fact, have lost an electron. That's what they have in common with one another. And because they lost that electron, they all have a +1 charge in that column. That's why they're put in that column. Now, we're going to go back over to the right-hand side, In the right-hand side, if you move in one column to column number 17 there with fluorine, chlorine, bromine, iodine, antimony below that, in that column, they are all a -1 because each element in that column has atoms that like to say, I don't feel balanced on the outside, go out and it'll grab an extra electron and put it into that outer shell. And so because of that, they'll attract that electron from somewhere else. And because of that, that gives them a negative charge, a -1 charge, in fact. So if we take the periodic table as a series of columns that have pluses and minuses and so forth, the first column is a +1. The second column is a +2. So for instance, calcium +2. If you go to the right-hand side then, those are the noble elements and they have no reactivity whatsoever. They're balanced. But inside of that, they're a -1. So that's the fluorine column there. If you come inside from that, an extra column, those are a -2 because they've attracted 2 electrons to fill their outer shells to make themselves balanced. Okay, so those are -2. So you know about +1s, you know about +2s, you know about -1s, you know about -2s, and you know the noble gases. So these things react with one another. In fact, they're attracted to one another. So if you have pluses and minuses, they tend to gravitate towards one another. So we call this concept of having a plus charge or a minus charge as its valence. And so, in fact, in between those right-hand side and those on the left-hand side are the metals, and we call them transitional metals. So for instance, iron. Iron is identified by the symbol Fe. It stands for the Latin word ferrium. So ferrium or ferric also is another one. So ferrium is the name of the element, and ferric is when it has a +2 or +3 charge. It can have a variable charge, so it can sometimes be +2 and sometimes +3. So in the middle, they're kind of variable as to what their charges are. And so iron can be +2 or +3. Sometimes it's even +4. So there are different valences. And so that it refers to its electronegativity, or electrovalence, some people call it. Let me give you another example out of there. Cr stands for chromium. Chromium is the same stuff that's on the chrome bumpers. It's a plating, right? But it's a metal. And it has that reflective appearance to it, right? Chromium is one of the most toxic elements you can imagine. Sometimes it has a +6 charge. Now, +6 in the human body doesn't go together very well. And so very commonly, hexavalent chromium or +6 chromium is very reactive with the human body. In fact, probably also the +4 version of chromium as well. So there is a variable valence to each one of these in the middle part here. And those are the transitional metals, of what they call them in the periodic table of elements here. But on the left-hand side, those are +1. The next column, +2. You go to the right-hand side, they're balanced, the noble gases, and then it's a -1, -2 for oxygen and so forth. So they tend to attract one another. So we call these things, first of all, ions. Ions are atoms that have gained or lost an electron to achieve a stable balance. It's kind of like a wheel weight. It can't spin properly unless it's balanced. And so in order to have a balance, it's got to have at least 2 in that outer shell. And so that doesn't work very well if it's only one that's out there. So it grabs an extra one if you need it, and that's on the right-hand side here. On the left-hand side, it's like they just have one extra one out there. It's like, well, let's lose that one. So they lose their electron to achieve that spin balance, if you will, in the outer shells of their structure. And so those are the +1s on the left-hand side, the -1s over here on the right-hand side. If you come into the second column, -2s next to those. Those are ions. Ions have gained or lost an electron in order to have stability in their outer shells. The positive ions are called cations. I have cats. I got 3 cats. So I'm very familiar with cations. They're very positive. Let me put it that way. On the other side, they call them anions. Anions are the ones that are negatively charged. So cations and anions are attracted to one another. We're going to talk about that in a second. We call that bonding. because sometimes they can come together and form something new, made out of two atoms, and we call those things molecules. So that is the next, I've got some various abbreviations here to show you. So I tell you what: hydrogen, nitrogen, hydrogen, helium, carbon, if you go up and down on these things. So nitrogen, oxygen, sodium, so forth. So those are just some of the symbols that we use. Some of them are not straightforward. Okay, so for instance, if you were asked what gold is, it's actually Au. That stands for the Latin word aurelium. Aurelium means gold. You may be familiar with a very famous philosopher. His name is Marcus Aurelius. Well, he was the emperor of Rome, and he took his name from his golden status, I guess, so Marcus Aurelius. Argentinium is Ag, and it's also commonly known as silver. So Argentina is a nation that was founded because of its, named for its silver content. A lot of silver mines in Argentina. So all these other ones. So for instance, aluminum is number 13, the atomic number 13, with a weight of 26.982. Aluminum, if you go to Britain, they're going to call it aluminium, which is actually the proper pronunciation for it. Aluminum was introduced into the American lexicon by an aluminum foil company. So they wanted to market it, and they thought that aluminium was too tough to pronounce if you're an American. Okay, so we go down the list. Chlorine, K is actually, I don't recall what it is immediately here, but that is potassium. So K stands for that. Ca is calcium, and Fe, of course, is ferrium or iron. When we talk about the spins on these electrons and we talk about their orbitals, it's a little bit like a Russian doll. And so there are different levels at which these electrons spin around the nucleus. So that electron cloud has some complexity to it. We like to call the first orbital the s orbital, and then after that it's called the p orbital, and then beyond that it's called the d orbital. There's a whole bunch of different orbitals because you can have a whole bunch of electrons on the outsides in the electron cloud. I like to think about it is if you open up these like Russian dolls, you will actually see one layer and then another layer and then another. And when you finally get down to the middle, it's very small. And that's the s orbital. That's the tight orbital that's on the inside here. So the p orbital, you could think about it like a barbell. And so it's actually two pieces to it stuck together. And they're in three different dimensions. So you could have like a jack, so like a ball and jack. If the s orbital is the ball, the p orbital are the jacks. So there are 6 parts to it. So there's 2 heading this way, 2 that way, and 2 this way. With the d orbital, it gets a little more complex, and so you can do like a clover leaf, if you will. So there's like 4 of those levels that are like a clover leaf, and then the 5th one, it's just crazy. It's like a donut around the barbell here. So that is more or less the electrons and how they spin around the nucleus. For the next part of this, I get my recording up here to make sure everything's going okay on it. So that's the orbitals. And so the next part is they have to be balanced. And you've already seen the ones that are reactive and which aren't reactive. So we go on to where they're attracted to one another. So the cations are attracted to the anions. So the plus charges. It doesn't have to be 1-to-1. But that is the common one that we use to show that attraction. So we usually use sodium and chlorine because those are the most common ones that you may be familiar with. You know it as salt, actually. So sodium chloride is table salt. It's commonly called table salt. And so sodium and chlorine, sodium has a +1, chlorine has a -1. Because of that, they're attracted to one another. But in salt water, they're not attached to one another. But imagine if you had salt water and you evaporate it, you're going to get these ions closer and closer to one another, and eventually they're going to link up. And when they do that, they form a molecule. That's called sodium chloride. And so it's a bond that they have when they finally get close enough to lock up with one another. And they do that in a systematic and regular fashion. So it goes chlorine, sodium, and they link up like that, and they form larger structures. So in these molecules, they have this tendency to form shapes that are very, very regular. And so you know what a salt cube may look like. If you ever look under a microscope at a salt grain, you're going to see that it's square or more or less square. And that's what you see in this photograph here. You can actually see how they're kind of cubic in form. And in fact, that's the shape that they have as a mineral. So you're going to learn that salt is actually a mineral as well. And you're going to learn the geologic name for that, or the mineral name for it, which is halite. Halite is made out of sodium and chlorine. And so that is what you get here with salt. The linking of the small sodiums and the large chlorines together, and it forms a cubic shape because of that. So that cube has three sides on three different parallel sides, I should say, and that's going to affect its properties. So that is sodium chloride right there, or table salt, or halite, and the chemical formula for it is NaCl. So sodium chloride is the chemical name for it. So that is bonded together because of the plus charge on the sodium and the minus charge on the chlorine. So yeah, that's one type of bonding. It's called ionic bonding because they're made out of ions, right? So the cations +1, the anions -1. And so there's another type of bonding as well, and that's called covalent bonding. Now, we already talked about these shells, right? So the electron shells are on the outside. Sometimes, for instance, like oxygen has a difficult time because it has to pull in an extra couple of electrons to make it stable, but that makes it very reactive. Well, in the atmosphere, what it commonly does, it links up with another oxygen in order to form some more stable sort of molecules in the atmosphere. It's a gas, of course. So O2 is the stable form of that in the atmosphere. Nitrogen does the same thing. So that is a form of bonding that's a little bit different from the ionic bonding. It's called covalent bonding. One of the more common one, actually, you may be familiar with carbon dioxide. So carbon dioxide, carbon, there's one of those. Dioxide means there's two oxygens on it, and what it does, it forms a chain. So there's an oxygen, a carbon, then an oxygen, and it forms a straight line. And so what happens is the carbon will actually share its electrons with the electrons that it wants to lose. It'll share those with the oxygens. And so it forms a very stable molecule called carbon dioxide. It doesn't break down hardly at all. Ionic compounds, or ionic molecules, on the other hand, tend to break apart pretty easily. Just add water. For instance, if you add water to salt, it's going to dissolve. So you can break the bonds when you do that. So when you dissolve it, you break the bonds. And it gives off some heat, actually. So with salt, you put salt on ice, right? So it's actually breaking the bonds of the salt, and it gives off heat, and it melts the ice, turns it back into water. So for instance, with carbon dioxide, it's very difficult to break carbon dioxide apart. You can do it chemically, but that's about the only way to do it. And so those are called covalent bonds. The hardest substances we know are actually covalent bonds. And so actually a diamond is the hardest substance known to mankind. And so in a diamond, it's just carbon, and carbon with its excess of excess of 4, it bonds with itself. And so when it does that, it makes a very, very tough bond. Sorry, choking up a little bit here. That's diamond. That's my favorite mineral, by the way. So actually gold's right up there too. So if we look at covalent bonds, those are the ones that are most difficult to break. And those are the ones that are really good for forming rocks. The ionic bonds can form rocks as well, and everything's kind of ionically charged when you think about it. But in fact, the very toughest bonds to break are the ones that are covalent. We're going to talk about that more when we get to minerals, but for right now, I just want to leave you with this. There's a certain group of molecules that have characteristics that they're found in nature. They weren't alive. They're actually naturally forming, in other words, in the natural world. And they have to be solids, in fact, and they have to have a crystalline structure. So for instance, salt is one of those. Halite is a mineral That is, it occurs naturally in certain evaporative sort of situations. So there are certain combinations or certain molecules that can form up either ionically or covalently. They are inorganic, that is, they weren't alive at some point. They're made out of solid materials, not a gas or a liquid. And they have a crystalline structure like sodium, for instance, sodium chloride, for instance. So that's a cubic sort of structure that it forms. But every mineral has that sort of capacity to have a certain characteristic form or characteristic forms. It can have more than one form. And they also have a certain chemical composition. So those are the five parts of what it takes to make a mineral. We're going to talk about minerals again in the future here, but really there's about 4,000 of them. We're going to get into great detail on these things, and actually that's going to be one of the labs you have coming up here. So in summary, we have atoms that are the smallest indivisible part of an element. We have atoms that are composed of a nucleus and an electron cloud on the outside. The nucleus can have protons and neutrons in it. Neutrons are a neutral charge. Protons are a positive charge. Electrons are a negative charge that are spinning around the outside in that electron cloud. We can gain extra neutrons in a nucleus and turn it into an isotope. So isotopes are very easy to confuse with the other thing, which is an ion. So an ion can gain or lose electrons. Okay, so one of them deals with neutrons and the other one deals with electrons. So isotopes have a variable number of neutrons in the nucleus, and that gives them different weights. So for instance, carbon-13 or carbon-12 or carbon-14, those are isotopes. When we have the variable number of electrons in the outer shells, we're talking about the valence. And so what is the charge? So if you have a variable number and you have to lose an electron, we call that a cation. If you gain an electron, we call that an anion. And those are negatively charged because it's pulled in extra electrons into the outer shell. So those things tend to be linked together. So the cations and anions will tend to form up and form molecules. Those sort of compounds, if you will, are made out of molecules. And in geology, we talk about these things as minerals. So minerals have these five important parts. They're naturally occurring, they're inorganic, they're solid, and they have a crystalline structure and a characteristic chemical formula. So we're going to leave it at that. And so anyway, I'll catch you when we talk about minerals next. Thanks a lot. Bye now.